Welcome to Space Time with Stuart Gary.
Galactic cannibalism may finally be the clue to solving the mystery of the millions of missing stars at the centres of some of the biggest galaxies. A new study reported in the Astrophysical Journal, which examined the galactic cores of two of the largest known galaxies, has opened a new window into the processes that shape the evolution of massive galaxies. One of the study's authors, Professor Alistair Graham from the Swinburne University of Technology in Melbourne, says for the last few decades astronomers have noticed a star shortage in the centres of some of the biggest galaxies. Now, while investigating two large galaxies, each roughly 4 billion light-years away, almost a third of the way across the universe, Graham and colleagues may have finally solved the cosmic whodunit. And believe it or not, the main culprits aren't the usual suspects. The larger of the two galaxies, known as 2 Mass X J17222717 plus 3207571, is some 75 times more massive than our own galaxy, the Milky Way, and is the brightest galaxy in a huge galaxy cluster located in the direction of the constellation Hercules. The other smaller galaxy, known as 2 Mass X J09194427 plus 5622012, is near the constellation Ursa Major. It contains a slightly smaller galactic core, but overall it's still some 30 times more massive than the Milky Way. The authors have confirmed that one of the depleted cores in these two galaxies is the largest ever detected, and they believe it may not have formed in the manner previously thought. In normal-sized galaxies such as the Milky Way, the density of stars tends to increase smoothly as you move towards the galactic centre. However, the less massive of the two galaxies being observed by Graham and colleagues appears to contain a smaller depleted core, likely formed by the collision of two similar-sized galaxies, each seated with a central supermassive black hole several billions of times the mass of our Sun. In these galactic collisions, the supermassive black holes from each of the two colliding galaxies tend to migrate towards the centre of the newly created merged galaxy by flinging out the stars already there, literally hurling them outwards in a gravitational tidal slingshot. Meanwhile, those stars less fortunate, which venture too close to the black holes, are likely to be ripped apart and swallowed, disappearing forever beyond the black hole's event horizon. These cataclysmic events produce high-energy ultraviolet and X-ray flares, as each star's multi-million-degree core is exposed as it's shredded by the immense gravitational field surrounding each of the black holes. Graham says when the black holes themselves finally merge, a series of gravitational waves are also emitted. However, simulations have shown that if a galaxy collision involves a larger galaxy consuming a smaller satellite galaxy, a process called galactic cannibalism, things can be somewhat different. If the captured smaller galaxy has a densely crowded centre of its own, then this tightly bound central region can survive largely intact during the cannibalistic affair, with only the outer stars being stripped off. During this process, the captured galaxy migrates towards the centre of the larger galaxy in a braking process that literally pumps stars out of the core of the larger galaxy. Computer simulations have shown that they do this in such a way that a core of constant stellar density is created, around which the semi-digested stars then hover. Unlike the smaller of the two galaxies studied by the team, the stars in the core of the bigger galaxy are uniform in their distribution, and this galaxy also contains several dense knots of stars near the edge of its core. One of these knots measured a massive 45 billion times the mass of our Sun. Now, when you think about it, that's almost equivalent to the entire stellar mass of the Milky Way. Furthermore, the larger galaxy's giant core, discovered in 2012 by Mark Postman from the Space Telescope Science Institute in Baltimore, Maryland, is unusual in that it's some 10 times larger than those typically observed in other galaxies. Graham suspects this giant core was primarily formed from captured satellite galaxies, rather than massive black holes. Indeed, the culprits appear to have quite literally been caught in the act.
We've been studying two galaxies, and we thought from the beginning that the missing stars had probably been either eaten, swallowed whole, or gravitationally slingshot out of the centres of these two large galaxies. But one of the galaxies has such a massive depleted core, it's missing 100 billion stars, that black holes they weren't actually big enough to do so much damage. So we think different scenario may have unfolded. We think the large galaxy has captured some of its nearby satellite galaxies. Now, in so doing, the galaxies themselves, they fall towards the centre, but they do so in a process which ejects stars out of the centre of the large galaxy. And we can see in the Hubble Space Telescope image remnants of 5 galaxies which have been partially digested by this large galaxy hovering around the core of this big galaxy. So that is, we think that we've observed the culprit for depleting the massive core.
You were seeing this using the Hubble Space Telescope, and to me this is the mind-blowing thing about it. This thing is a third of the way across the universe. It's 4 billion light years away. That's amazing.
Indeed it is. It's very far away. So what we observe today actually happened 4 billion years ago, but it's taken light that much time to travel across the universe to reach our telescopes. It also means that if we were to transport ourselves to the galaxy we are observing, that is, if we were right on its doorstep today, it's had 4 billion years to evolve, and the core could be much greater than what we observe.
Because that's almost the age of the solar system when you think about it, 4 billion years.
It is. A lot can happen in that time.
That big galaxy wasn't the only one you looked at. There was another one about the same distance away towards the constellation Ursa Major too.
That's right, yes, the Big Dipper. A little hard to see from Melbourne, but if you're in the north of Australia during the summer months, you can actually get a glimpse of that. Although the targets that we're looking at, they are very faint. So you can see the constellation, you can look in the direction of the galaxies we've been observing, but you won't actually see them with your naked eye. I will add, the smaller galaxy that we observed, it also is missing a lot of stars from its core, but the amount of stars which are missing, we think that massive black holes, that is, black holes with 1 billion times the mass of our Sun, we think they could have caused the damage in that galaxy. But in the larger galaxy, with the very large depleted core, and when I say very large, it's about over 20,000 light years across, 100 billion stars missing, we think that the infalling satellite galaxies, which are bigger than massive black holes, they can be 10 or 100 billion solar masses, the galaxies, and therefore being more massive, they can cause more damage. We think that these infalling satellite galaxies have removed the stars from the centre of this giant galaxy with the giant partially depleted core.
Is this really another form of environmental quenching?
It is in a way. If you are a galaxy that is forming stars, if it has gas which can condense and form new stars, if that galaxy was to fall into a big galaxy, it's going to lose the ability to hang on to its gas, and so it loses the ability to form new stars.
So it's the same sort of gravitational process at work here.
It is. We call it a range of things, stripping of the gas. Sometimes astronomers use the term strangulation.
Well, that's a good one. I like that one.
That's a choking off of the gas supply in the halo of a galaxy. There are others.
Were you guys suspecting there must be another possible cause for this dearth of stars in the galactic centres of some of the biggest galaxies, simply because black holes couldn't explain it, so there had to be something else doing it?
Yes. The biggest thing which tipped us off and made us look into this system was the extent of the partially depleted core. Being over 20,000 light years across, it's roughly 10 times larger than the sizes of partially depleted cores in other big galaxies. So the first thing we wanted to do was to check, is there really such a large depleted core in this galaxy? Modelled the galaxy, subtracted off all of the foreground and background contaminant stars that one sees in these images, and measured the distribution of light in the star, convinced ourselves that indeed there is a very large deficit of stars in the galaxy, and then we thought, this is so big, black holes are probably not the culprits responsible for causing the damage to the heart of this galaxy.
And as you were looking at these stars in the larger galaxy, or the lack thereof, you saw these massive, you've described them as dense stellar knots. And some of them, I mean, these figures are amazing. 45 billion times the mass of our Sun. That's like the stellar mass of our entire galaxy, isn't it?
You're right, that is. And those galaxies were probably bigger. What we believe we're seeing, these knots of star clusters, they are the semi-digested galaxies which the larger galaxies captured. So they could have been twice as big. What's happened is the stars in the outer part of these captured galaxies have been stripped off as they've fallen into the large galaxy, a bit like evaporation, if you like. And what's left behind is the tightly bound nucleus or core of the captured galaxies. We've seen 5 of them, which means there are 5 galaxies that have fallen in and can act on depleting the stars from the centre of the large galaxy.
And of course, these events, these galactic collisions, they're not just something that happens in the distant universe. All galaxies seem to grow through merging or cannibalism, and that includes our own Milky Way, both in the past and in about 3.8 billion years from now, with Andromeda in the future as well.
Yes, that's right. The universe is a violent place. It was and it still is. Nature doesn't seem to have any morals. The big prey on the small.
As we look around, we're seeing lots of these tidal streams of stars, which is clear evidence of mergers.
It is indeed true. Mergers, we've always known they occur, but we're now starting to, I think, more fully appreciate just how important they are in building up galaxies over time. And one thing which wasn't fully appreciated was that mergers, if you have two galaxies of a comparable mass collide, we used to think, oh, you're going to end up with a big mess. You'll end up with an elliptical-shaped galaxy. But it's not always the case. Sometimes you can form a disk. So you have a central bulge of stars surrounded by a disk of rotating material. And so the mergers can actually give rise to ordered motion in galaxies, which wasn't always appreciated before.
We're finding out a lot about galactic evolution through these sort of studies, aren't we?
Oh, yes. We haven't got all the answers yet, but some things are coming into focus. One thing which I think hasn't been fully appreciated in the past is the formation of disks in galaxies. We used to think if mergers occur with infalling systems at random orientations, you'll just end up with a big mess, a big elliptical galaxy. But the way the universe seems to work is that the infalling captured galaxies, they tend to line up in a plane and contribute to the growth of disks in galaxies. So we have this structured, ordered rotation rather than simply a big mess.
That's Professor Alistair Graham from the Swinburne University of Technology in Melbourne. And it's worth pointing out that the future James Webb Space Telescope, expected to be launched aboard an Ariane 5 from the European Space Agency's Kourou spaceport in French Guiana in 2018, will enable astronomers to better image more galaxy cores and hopefully reveal just how often hapless satellite galaxies are consumed.